Yes, class. As I told you yesterday, I'll be starting with EMI today. So, basics of EMI, let us revise. Firstly, you have to understand the concept of magnetic flux. Magnetic flux is the number of magnetic lines of force crossing a surface normally. That is known as magnetic flux, which is linked with the surface. So, magnetic flux's formula is B dot A, which can be written as BA cos theta. This is how we take it. And it's a scalar quantity. This has to be kept in mind. Also, the dimensions ml square a to the power minus 1 t to the power minus 2. But this is not very important to remember in class 12th. Then SI unit is Weber's. Weber's SI unit, you should be remembering it. And one more important thing, that 1 Weber is equal to 10 to the power 10 to the power 8 Maxwell. So SI unit is Weber's, and this is the CGS unit. Then you have the concept of EMI, that is electromagnetic induction. So it's the phenomenon of production of induced EMF. It's the phenomenon of production of induced EMF due to a change of magnetic flux linked with a closed circuit. All right, means the term electromagnetic induction means that inducing electricity, electromagnetic induction. Induction means inducing electricity, but the term is electromagnetic induction means inducing electricity through magnetism. This is what is EMI. Then in your board exam, especially in the 2-marker sections, you can get a question to write on the Faraday's laws of EMI. So Faraday's laws are important, where first law is there, and you have the second law. Basically, first law tells you the fact that whenever magnetic flux linked with the circuit is changed, EMF is being induced. It tells you the concept of EMF, that yes, EMF is being induced. Second law tells you the exact values of it, that this induced EMF, this is directly proportional to the change of magnetic flux, rate of change of magnetic flux linked with the circuit. Then you have a negative sign present here, minus. So minus is given by Lenz's law. Lenz's law tells you the fact that the direction of induced current is such that it opposes the cause which produces it. And what is the cause? Mainly that it opposes the change in flux. Clear? In the numericals, this is very often used. It is written as phi2 minus phi1 by t2 minus t1. This is most commonly used. And if number of turns are also provided, you have to multiply it with the number of turns. Then you have the concept of motional EMF. Motional EMF means the EMF that is induced when the body is in motion. Magnetic Lorentz force acts on the free electrons of the conductors. So you have E is equal to BLV. From there, you have the formula of force as B square L square V divided by R. And further, you have power, which is equal to B square L square V square divided by R. Clear? These are all the rules. What all things we have? Yeah, one more thing, class. One more formula-based question can come. Is charge, the change in charge is change in flux by the resistance. Net change in magnetic flux by the resistance. Because this we have done in the class. You can check also how we have obtained it. Then the last topic in EMF, in EMI you have is induction. So when we are talking about induction, so in induction, we have two types of induction. One is self-induction. Second is mutual induction. Second is mutual induction. So self-induction is the production of induced EMF in a coil when a changing current is passed through it. Right? That is self-induction. And you have the formula E is equal to minus L di over dt. In mutual induction, when we talk about mutual induction, it's the phenomena of production of EMF in one coil when the current in the neighboring coil changes. Suppose in this coil, if the current is changing, then the mutual induction is being produced. Formula remains the same. It's just that you have the coefficient, which is different. E is equal to minus m di over dt. All these things we have discussed. One more thing, both have their same SI unit, that is Henry. And 1 Henry is equal to 1 Weber per ampere. All right, lastly, you have the coefficient of coupling, which is K is equal to under root M by L1 into L2, which connects the two values of inductances, that is the mutual inductance and the self-inductance. Just one thing, remember, for coefficient of coupling, you have the values between 0 and 1. This cannot exceed it more than that. All right, these were all the basics in your EMI. Again, I'm putting all the things. You can copy down anything if you want to copy anything. Then I'll start with the numericals. All right. See, this question says figure 6.88. This figure, this is given, and this says that shows a long rectangular conducting loop of width L. Okay, this is the width L given. Mass M, resistance R, placed partly in a perpendicular magnetic field. This is the magnetic field. With what velocity? We have to calculate the velocity. Should it be pushed downwards so that it may continue to fall without any acceleration? See, suppose the frame falls with uniform velocity v. This velocity, we are assuming it to be v. All right. So EMF will be BLV. Motional EMF across the ends of the upper arm will be BLV. Current in the circuit will be voltage divided by resistance, that is BLV divided by the resistance R. When we are talking about the magnetic force, how do we write the magnetic force? With respect to the length of the wire, how do we write it? BIL. Remember, this is the force across the conducting wire which we've studied. Now, if you put in the value of current here, so force will be equal to B square L square V by R. You already know this, right? What you have to add is, look class, if the frame, it's a very, very short, very easy question. This is saying it is falling downwards. If it continues to fall downwards, means this entire setup, this is falling downwards. So which force is coming into action? Gravitational force. Gravitational mg force, mg will be coming into action. So F is equal to mg. So you can equate this force with this force, that is mg is equal to b square L square V by R. So what is the velocity? mgr divided by b square L square. This is the formula, this is the answer. Write it. Okay, see, this says that magnetic flux passing perpendicular to the plane of a coil directed into the paper is given by, this is the value of flux. Phi is equal to 5t square plus 6t plus 2. You have to calculate the magnitude of induced EMF set up in the loop at t is equal to 1 seconds. So we have to differentiate this, right? E is equal to d phi over dt. So on differentiation, we will get 10t plus 6 plus 0, right? 10t plus 6. And what is the time? Time is given as 1 second. So E will be 10 plus 6, which is equal to 16 volt. No, milliwebers. Okay, this is in milliweber, so this will be in millivolt. The final answer will be in millivolt class. Pay attention to the units that are given in the question. See, this was given in milliwebers. This is given in seconds. This, if this was also given in milliseconds, our answer would have been directly in the SI unit, that is Webers, without, because cancellation won't occur. But this is in milliwebers, so answer will also be in millivolt. Second part says that what is the direction of current through the resistor? Direction of the current through the resistor. See, for the second part, you directly have to apply Lenz's. Direction of induced current is such that it opposes the change in the flux. So for this, induced current should generate outward flux, right, by flowing in the anti-clockwise. Understood? It is telling, the magnetic flux. If you look at the figure in the question. Okay, figure is not given. So, but details should be given. Magnetic flux passing perpendicular to the plane of coil, all right? It is, if this is perpendicular, this is the setup, right? Now, direction of current through the resistor R. It means there is some coil which is present. With the resistor R. So direction of induced current will be to oppose it, right? Direction current should be to oppose it. Now, so if induced current has to generate outward flux, it has to move anti-clockwise, and induced current will flow from left to right. This would be the direction. Write it. This was a very easy short question. Some more questions we will see. See, a square metal wire of loop side 10 centimeter resistance is 1 ohm. So in this, the best way is that you reduce the circuit. If we'll find out the equivalent resistance, in this case, this is 3, this will be nullified. Remember in Kirchhoff's law, I've told you, Wheatstone bridge, because this is acting as a Wheatstone bridge. So this will be nullified, the central one. 3 plus 3, look, this is not existing. 3 plus 3, they are connected in series. 3 plus 3, they are connected in series. This is 6, this is 6. And further, this 6 and 6, they are connected in parallel. That again becomes 3. So equivalent resistance is 3. So 1 by R dash is 1 by 6 plus 1 by 6, which is equal to 1 by 3. So resistance is 3 ohms. Right? Now, one more thing. 3. Yeah, correct. Now see, it is saying that the resistance of the loop is also 1 ohm. The resistance of the loop is also 1 ohm. So it means 1 more ohm will be added. So equivalent resistance will be 3 plus 1, which is equal to 4 ohms. Right? Now come to your EMF, that is BLV. And current will be BLV by R. So what would be the speed from, what would be velocity from here? Velocity will be IR divided by BL. Current's value, now you just have to substitute everything. This looked difficult, this looked lengthy. The value substitution is easy. 1 milliampere, that is equal to 10 to the power minus 3 amperes. Length is equal to 0.1 meters. And magnetic field is equal to 2 Weber per meter square. So if you substitute, this is 10 to the power minus 3 into resistance we've calculated, that was 4 by 2 into this is 0.1. This becomes 2. So 2 into 10 to the power minus 2 meter per second. This is the answer. Write it quickly. Okay, this says that a small flat search coil of area 5 centimeter square. This is the area that is given, 5 centimeter square with 150 closely wound turns. This is the number of turns. Is placed between the poles of powerful loudspeaker magnet and then quickly snatched out of the field region. Total charge is given as 10.5 millicoulombs. Resistance is given as 0.6 ohms. What is the field strength of the magnet? So initial flux, when we are talking about, that is NBA. Final flux is 0. So the change in flux will be phi 1 minus phi 2, that is NBA. When we are talking about the charge is the change in flux by the resistance, which is NBA by R. From here, you can calculate the value of magnetic field. B is equal to QR by number of turns into the area is equal to 10.5 into 10 to the power minus 3 into 0.6 by, this is 140 into 5 into 10 to the power minus. So this is 0.09 Weber per meter square. Write it quickly. Yes, class, talking about alternating current because that completes with EMI. So AC is left, alternating current, and then you have the concept of direct current. And average and mean value you have to remember. So whenever we are talking about I average or E average, that is 2 by pi I naught, which is equal to 0.637 I naught. Then ERMS is equal to E naught by root 2, IRMS equal to I naught by root. Then we have AC circuit containing only resistor. So in AC circuit having only resistor, you just have simply E naught by R. And there you have the resistance, which is XL equal to omega L. That is the inductive reactance. Then you have the circuits where you have capacitor circuits consisting of only a capacitor. There, when you divide E naught by XC, you get it as 1 by omega CC is the capacitance. So this becomes the capacitative reactance. Then we have the values of impedance. Impedance Z square is equal to R square plus the resistance net square, right? And when we are talking about tan phi, this is equal to X by R, or you can say cos phi is equal to R by Z. Then LCR circuits you have to remember. When we are talking about LCR circuits, I naught is equal to E naught by R square plus XC square or XL square, whichever is required. It's better if I write this as E naught by Z. Z is the impedance, whichever circuit is there, that can be used. Or for impedance in LCR circuit, we can write it in this way also, R square plus omega L minus 1 by omega C whole square. All right. Then in resonance circuits, one more thing which we have to remember is the frequency. Frequency is 1 by 2 pi under root L by C. All right. Then you have the Q factor, which is the quality factor. That is the resonant frequency by the bandwidth. Bandwidth is written like this. So this is the bandwidth. And this is the resonating frequency. Resonating frequency. Then you have the concept of wattless current also we've seen, energy stored in inductor capacitors. And then transformers. For transformers, one relation is only sufficient. That is E2 by E1 is equal to N2 by N1 is equal to I1 by I2. That is enough. Just have a look at this, then we'll see the numericals. See, this question says that two bulbs B1 and B2 are connected in series with an AC source of EMF 200 volt as shown in this figure 7.71. The labels on the bulbs read 200 volt and 60 watt, 200 volt and 100 watt. Resistances of the bulbs R1 by R2. See, R1 is equal to V square by P1. R2 is equal to V square by P2. So R1 by R2 is equal to P2 by P1. That is 100 by 60. So this becomes 5:3, the ratio. When they are connected in series, we have to find out the power being consumed, right? In series, P1 by P2 we have to. So see, for the second part, this is the first part. For the second part, power is equal to I square by R1. Now we know this is the series connection. So in the second case, we need not change the current's value because current that would be flowing would be the same. Right now you can take the ratio P1 by P2 is equal to R1 by R2. Again, the same answer, that is 5:3. 5:3. Last one says potential difference across the bulb, that is V1 by V2. You have to calculate. See, third part will be voltage, apply Ohm's law, I R1, V2 is equal to I R2, right? So when you take the ratio V1 by V2, this becomes I R1 by I R2. I cancel. This is equal to R1 by R2, which is again 5:2. So answers for all the parts, this is 5:3. Write it quickly. Yes, class, time is up. AC questions, some are left that I'll discuss in the next class. So AC and EM waves also, this is left. So on Saturday, I'll discuss. Thank you so much, class.